Okay then, for this part of the question, we've got to work out gg of 5 given g of x is equal to this equation here. So all we need to do is just substitute, first of all, 5 for x in g of x. That means we're going to have g of, I'll put this in a square bracket here, g of 2 times 5. We'll show a little bit of working as well. 2 times 5 plus the 5, and that's all over 5 minus 3. Okay, so just close that off there. And if we work this out, we've got g then of, and we've got 10 here plus 5, that's 15, divided by 2, which is going to be 7.5. And if I now substitute 7.5 in for x, we're going to have 2 lots of 7.5. Again, I'll just put the working in, plus the 5, and that's all over 7.5 minus 3. And if you work this out, 2 lots of 7.5 is 15, plus the 5, that's going to be 20, and that's divided by 4.5. So what I'm going to do now is just double top and bottom, and you get the exact value of 40 over 9. Okay, just leave it like that as the exact value. Okay. Now for this part of the question, we're given g of x, where x is greater than or equal to 5, and asked to find the range. Now, if you've been watching my earlier tutorials on range and domain, you'd know that to do questions like this, I always suggest that you sketch the graph. Without the knowledge of the graph, it's very difficult to, in my opinion, to find the range and domain. So if we just set up some axes, something like this, okay, we've got the origin here, then looking at this graph here, we know that when x is equal to 5, we saw in the last part that g of 5, let's just write it in, g of 5, that was just by substituting x equals 5 in here, gave us 7.5. So we've got our starting value. So if I take this point here, let's say as being 5, just mark that in there, we know that we've got 7.5, so let's just say it's about there-ish, okay? Let's just mark that in as 7.5. Okay, it's not to scale, but just give you an idea of the graph. Now, when I look at g of x, we can see that it is 2x plus 5 over x minus 3. I don't like the look of that. It looks very complicated to sketch. So what I'm going to do is just divide top and bottom by x, so I can see what the behavior is as x gets larger. So 2x divided by x, well, that's just going to be 2, and then we've got the 5, and that's divided by x, so we'll put that as 5 over x, and we'll have that all over x divided by x, which is 1, and then you've got minus 3 over x. And changing it into this style makes it a lot easier to see what happens as we let x get larger. So I'm just going to write this in here as g of x, okay, for x tending to plus infinity. Well, what we're going to get here is this term here, 5 over a very large positive value, that's going to tend to 0. So in the numerator, we're going to have 2. And in the denominator here, okay, we're going to have 3 divided by a very large positive number. That's going to tend to 0. So we're just left with the 1. Now, really, as x gets larger, it's not going to equal 2 over 1. It's going to actually tend to 2 over 1. In other words, 2. So what I've got here is a positive asymptote, y equals 2. And I can see that when x is greater than or equal to 5, the top here, this term here, is always going to be positive. So adding it to a positive number, that top here is going to be positive. 3 divided by a positive number, always going to be positive. It's going to be less than 1, so we're in the denominator, we're just going to have a positive value. So in all, positive divided by positive is positive. This graph is always going to be greater than 2. So our graph is going to go from 7.5, and as x increases from 5, it's going to approach that asymptote there of y equals 2. So what's our range going to be? Well, we can see from the graph it's going to be anything greater than 2 up to 7.5. Okay, so if I put for that range g of x there, we can see that it's always greater than 2 but less than or equal to 7.5. Alright, so hope you've been able to see your way through that if it was causing any problems. Typical question then on range for a function. Now in this last part of the question, we're given our equation then, g of x, where x is greater than or equal to 5, and asked to find the inverse of g and also to state its domain. Now when it comes to working out the inverse function, what I like to do is just say let x equal, and wherever there's an x in the equation, just change it to a y. So we've got 2y plus 5 all over y minus 3. And what we're going to do now is just make y the subject. And what I can do then is just multiply both sides through by y minus 3. So we're going to get x times all of y minus 3, and that's going to give me xy minus 3x, and that's going to leave me with 2y plus 5. Okay? Now, all I need to do is group the terms containing a y to one side, and I'm going to add the 3x to the other side. So let's subtract the 2y from both sides, and I'm also going to imagine pulling out y then as a common factor. So we've got y multiplied with the x here, and then we've got minus 2y, so we'll put minus 2 there, and that's going to equal the 3x plus the 5. Okay, so all I did there was just add 3x to both sides and subtract 2y from both sides. Next, I'm just going to divide both sides then by x minus 2, and that's going to give me 3x plus 5 then all over x minus 2. And now that I've got what y is, I can replace that y with the inverse function of g to the minus 1 of x, okay, as I call it. And that's going to be then 3x plus 5, if we just copy that back down, 3x plus 5 all over x minus 2. And next then we have got to work out the domain of the inverse of g of x. Now to do this, you should realize that the domain of this inverse function is in fact the range of g of x. And we worked this out in the earlier part of the question. If you're unsure of this, I've got it in tutorials, but essentially it's based on this idea that if you have the graph, in this case of g of x, which we worked out in the previous part of the question, then if we reflect this in the graph y equals x, this diagonal here, then this asymptote here becomes a vertical asymptote, and if I draw that in, that asymptote is x equals 2. And we reflect this graph here in y equals x, and you're going to get this image here. So you'll see that the 7.5 that we had here ends here on the green graph, okay, of the inverse of g of x, and it approaches this asymptote here. So when it comes to that domain, can you see that the domain now goes from x is greater than 2 but less than or equal to 7.5. If I just put that in there, that's your answer, And you can see it's exactly the same as what we had for the range of g of x. Okay, so hope that's given you an idea on that question. Okay, so for this question then, we're given the position vectors of A and B, and also told that the vector AB equals the vector BD, and we've got to find the position vector of D. Now, whenever I'm doing vector questions, say something like this, I always find it a good idea to sketch a diagram. And so with that, I'm going to just say that we've got our origin, say here, and just pick a point. Let's say this is the position vector of the point A. I'll just mark the coordinates in of A. That would be 2, 3, minus 4. And this will be the origin. Notice you can just draw this anywhere you like. It doesn't matter, okay? So I'm often asked, where do you put this? Just anywhere, okay? It doesn't matter. Now we've got the position vector of B. So I'm just going to say then that, let's say it goes from here to, let's say, that point there, okay? And that's the point B, and I'm marking its coordinates as 4, minus 2, 3. And we're told that A to B equals B to D. So in other words, if we look at A to B, which would be a vector in that direction, then if it's got to be the same vector, it's going to be from B to D, it's going to be the same length in the same direction. So I would say D would be somewhere there, okay? These two lengths would be exactly the same, and the position vector of D would be given by this vector here, O to D, all right? This will be the point D. Now, we've got the diagram. Should be fairly straightforward to visualize what's happening. If we're going to aim to get that vector O to D, how can we get from O to D? Well, it can be O to A plus 2 lots of A to B. So if we just put that in, O to A plus or followed by 2 lots of A to B. Now, when it comes to A to B, okay, let's just put this in. A to B, standard result, okay, it's going to be the same as O to B minus O to A. All right. You can see it from the diagram actually. If you're going from A to B, it's in the reverse direction of O to A, so that's the minus OA and plus OB. I've just changed these around, okay? OB minus OA. Now, all I need to do is just say open up this bracket here, and you can see that I've got 2 lots of O to B. So we've got 2 lots of O to B, and then we've got O to A minus 2 lots of O to A, so it's going to be minus O to A. And all I need to do now is just fill in our values. We've got 2 lots of O to B, and O to B, I'm going to write it as a column vector. This time is 4, minus 2, 3, so you've got 4, minus 2, 3. And we've got minus O to A, and O to A will be 2, 3, minus 4. 2, 3, minus 4. And if you work this out in the usual way, you're going to end up with 8 here, minus 2, which is 6, and you've got minus 4, minus 3, so that's minus 7, and you've got 6 here, plus 4, that's going to be a total of 10. So there's your column vector. You can either leave it like that, or you might want to write it in i's, j's and k's. So that's going to be 6i, I just underline the i's, minus 7j, and then plus the 10k. All right, so hopefully you've been able to see your way through that one. Okay, so for this part of the question then, we have been given the vector OC in terms of this value a, where a is less than 0, and also given that the modulus, the distance from a to c, is 4 units, so we've got to find a. Now in the previous question we had this diagram, and really we don't need the majority of this. All we need is the vector O to A. So I'm just going to remove that, okay, and that will leave us with the vector O to A. So if we're to work out the value of A, how are we going to do it? Well, we know that the modulus of AC is 4 units, so that means that the distance from A to C is going to be 4 units, and it can lie anywhere on a circle with A as centre. If I draw that in, it's going to be there. So the point C can lie anywhere on the circumference here. Now it doesn't matter where I place this, just for the purposes of working this out, okay, but let's say I put C at this point here, okay, let's just call that C. So this is the position vector of C, O to C, and we know from A to C, well, that is 4 units. So what I'm going to do is work out the vector A to C, and then I'm going to use this result, okay, by using Pythagoras' theorem and form an equation that equals 4, and should be able to solve that and work out what the value of A is. So the first thing I need to do is get the vector A to C. So in the usual way, the vector A to C is going to be O to C minus O to A. Okay, so A to C down here minus O to A followed by O to C. O to C minus OA, all right? And we can use, say, column vectors here. O to C we know is this vector, and we've already got the vector O to A. It's going to be 2, 3, minus 4 if written as a column vector. So if you do that, writing those column vectors in, doing the subtraction, you should end up with A minus 2, 2 and 2. All right. Now we start to use this result here, the modulus one. So I'm just going to write in here again, all right, that we've got since the modulus of A to C equals 4 units. Well, using Pythagoras' theorem, it would be the square root of all of A minus 2 squared plus 2 squared plus 2 squared equals 4. But what I'm going to do is square both sides of my equation. It just avoids using the square root sign, okay? I'm just going to say that that modulus, if you squared it, is going to equal 4 squared, which is going to be 16. And what that means then is that the sum of just the squares of that vector A to C must equal 16. So that's all I'm doing there, okay? Just summing the squares of these components here. Right, okay, so I could square this bracket out, but that's up to you. You don't really have to do that because it's much easier just to know that this is 4 and 4 here. Total of 8. Take 8 from both sides and you end up with, therefore, all of A minus 2 squared equals 16 take 8, which is 8. And all I need to do now is just square root both sides. And that will leave me with A minus 2, and that's going to equal plus or minus the square root of 8. Now I could break this down to an exact value just by saying, well, this is the same as the square root of 4 times 2. The square root of 4 is 2, and we're just left with root 2 like that, okay? 2 plus or minus 2 root 2 then. Now, if I add 2 to both sides to get A will equal 2 plus or minus 2 root 2. And we know that A is a negative value, it's less than 0. So which one of these results gives us a negative value for A? Well, it's going to be A equals 2 minus 2 root 2. Okay, and that's because, I'll just put here, since A has to be less than 0. All right. Okay, for this question then, we've got to disprove this statement by a counterexample. That is that if m and n are irrational numbers, where m doesn't equal n, then m times n is irrational. And what I'm going to do is give you 3 examples, for instance, just to show you how this can be done. The first example is just to take an irrational number. First one that springs to mind, for instance, is say the square root of 2. And you could just now take any multiple of root 2, like for instance 3 root 2. And working backwards, if you were to think of 3 root 2 as being the square root then of 3 squared, which is 9, and just times the irrational number root 2, okay, we can think of it as the root of 9 times 2. Square root of 9 then is 3, and then you just got the square root of 2. And this is exactly the same as the square root of 18. So what we've got here is the square root of 18 is an irrational number based on root 2. Okay? So what you'll notice now is if I take the root 2 here and multiply it with the irrational number root 18, we now have the square root of 2 times 18, 36 in other words, which we can get the exact square root from, which is going to be 6. A rational number, not irrational. Okay? Look, let's do another one. Again, let's think of an irrational number, let's say root 3 instead of root 2. So if we've got root 3 here, think of another multiple of root 3. Let's say we take 3 root 3. Okay, 3 root 3. Where does that take us? Okay, well, this came from the square root of 3 squared, this 3 squared here, which would be 9, times the 3. Okay? And 9 threes, 27. So therefore you've got the root of 27 would be an irrational number. And the nice thing is now that if you do root 3 times the root of 27, you end up with the square root of 3 times 27, which is 81. And as we know, the square root of 81 is 9, a rational number. So what I'm doing then is taking any irrational number from its root. Okay, you could use root 5 if you wanted to as another example, and then multiply it with a multiple of that rational number. Okay, and you should find got a good example there to give. I did say I'd give you 3 examples, so I'll give you another one here, totally different now. This one here is, for instance, if you took the well-known irrational number pi and you multiplied it, for instance, with 1 over pi. Those pi's would cancel and it would just leave you with 1. Okay, so here we go. Then we've got 3 examples, and if you were to write a conclusion, then you can see that so if m and n are irrational numbers, then m times n is not always irrational. Okay? Now in this question, we've got to, first of all, sketch the graph of y equals the mod of x plus 3, and then explain why the mod of x plus 3 is always greater than or equal to all of the mod of x plus 3 for all real values of x. Well, first of all then, if we've got to sketch the graph of y equals the mod of x plus 3, you should be familiar with the graph of y equals mod x alone. Here it is, here, okay? It's based on the graph of y equals just x alone, which would be a diagonal like this. And remember that whenever you've got any negative values of y, okay, then they're going to become positive values, so you get a reflection in the x-axis like so, okay? So the graph then of y equals the mod of x, it's symmetrical about the y-axis. Now when it comes to adding 3 more, we just translate the graph, because we're adding 3 more to the y value, we just translate it upwards. So you're going to get basically something like this happening. This is going to move upwards, let's say there, 3 more units. And what we end up with then is the graph of y equals the mod of x plus 3. And there we have it, okay? Might want to actually put in that this point here on the y-axis is 3, okay? Now, if we've got to explain why the mod of x plus 3 is greater than all of the mod of x plus 3, then let's just draw the graph of y equals the mod of x plus 3. If we were to draw the graph of just y equals x plus 3, then that graph is going to look something like this. It would come from here, it would lie on top of this graph, okay, and it would come all the way down and pass through the x-axis at -3 all the way down like this, okay? So let's just draw that in, something like this, okay? Meant to be on top, it's just missed it there. It will cut the x-axis at -3, but when we take the modulus, these negative values here are reflected in the y-axis, so you're going to get something like this, okay? And that will be the graph then of y equals the mod of all of x plus 3. So, can you see now that from this graph, I'll just make that line a little bit thicker there, okay? Something like this, let's just do it a few more times, there we go. All right, okay. If we take any value of x, let's say we take a value of x here, if we were to substitute it into this graph and into this graph here, they'll give us exactly the same value, okay? That's for values of x greater than 0. But when we take values of x less than 0, can you see that for any value of x, let's say we took this one here, we would get this value if we were to substitute in the mod of all of x plus 3, but we would get a greater value if we were to substitute it into just y equals the mod of x plus 3, because this graph is above this graph here when we take negative values of x. So in summary then, you can see that since the graph of the y equals mod of x plus 3 is always above or equal to the graph of y equals the mod of all of x plus 3 for all corresponding values of x, then this statement, the mod of x plus 3, is always greater than or equal to the mod of all of x plus 3 for all real values of x. All right? So for this question then, we've got to show that sigma going from r equals 1 to 16 of this expression here equals 131,798. So how do we do this? Well, let's start with copying down the question. And what I'd want to do next is expand this across these 3 terms. If we do that, then we've got this result here, okay? The summation are going from 1 to 16 of the 3. Notice how on the second term I've pulled out that constant 5, okay, from here. 5 times the summation of just r going from 1 to 16. And then I've got the last term, the summation of r going from 1 to 16 of 2 to the power r. So what have we got here? Well, with the first term here, I've got 3 repeatedly added 16 times. 16 lots of 3 then being added. When it comes to this next term, if I break this out, we've got 5 times all of, and r goes from 1 to 16. So when r is 1, we've got 1. When r is 2, we add 2. When r is 3, we add 3, and so on. And this is just going to go up all the way to the last term where we add 16. And on this last term here, we've got to add 2 to the power 1 when r is 1, 2 to the power 1, plus when r is 2, 2 to the power 2, and so on, 2 to the power 3, plus all the way up to when r is 16. So that's adding 2 to the power 16. Well, we know that 16 times 3, that's easy, that's 48, so we'll just do that. Now here we've got 5 times the sum of all of these terms in the bracket, 1 plus 2 plus 3, etc., all the way up to 16. Now what I notice here, this is an arithmetic progression, or an arithmetic series actually, because we're adding terms where we've got a common difference of 1. Okay, we add 1 to each term. First term is 1 and the number of terms is 16. So you should be familiar with the formula for the sum of an arithmetic series. If not, do check out my videos on this. So according to the formula, it's n over 2, so that's going to be 16 over 2. I know that's 8, but I'm just going to show the working here. I'll put a square bracket there. It's twice the first term, 2 times the 1, which is the first term, okay, plus n minus 1 times the common difference. N is 16, take away 1, that's going to be 15. The common difference is 1, we're adding 1 to each term. Okay, so there's our summation for the arithmetic series there in the bracket. Now when it comes to this next bracket, should recognize this as a geometric progression. We're continually multiplying by the same value, 2. And the sum of a geometric series, you should also be familiar with this. Sn is equal to the first term a times the common ratio r to the power n minus 1, all divided by r minus 1. So if we fill in our values for that, we have got the first term, which is 2, okay, times r to the power n. That common ratio r is 2 as well. We're multiplying each term by a value of 2. So it's 2 to the power 16, r to the power n, minus 1, and that's all divided by r minus 1. 2 minus 1, which is 1 there, okay? So just a question of working these out. We've got 48 then as the first term. If you work this out, we've got 2 here plus 15, that's 17. Multiply it with the 8 and you should find you get 680 when you finish multiplying with the 5. So that's 680. And if you work this out on your calculator, you'll end up with 131,070. And if you add all of these 3 terms together, you end up with the result we've got to show, 131,798. All right. So for this part of the question then, we've got this sequence of terms, u1, u2, u3 and so on, where any term in the sequence is equal to 1 divided by the previous term in the sequence. And we're told the first term, u1, is 2/3. And we've got to find then the sum of the first 100 terms of that sequence. So we've got this. Remember, this represents u1 plus u2 plus u3 and so on, all the way up to u100. And if we start filling this in, u1 being the first term, we see it's 2/3, and then u2, using this result here, is 1 divided by u1. So we've got plus 1 divided by 2/3, which is 3/2. You just need to invert the fraction. And then when we get to u3, that's going to be 1 divided by u2. 1 divided by 3/2, again just invert the fraction, that's going to be 2/3. So clearly I can see that we've got a pattern emerging here. When it comes to u4, we've got 1 divided by u3, 1 divided by 2/3, back to 3/2 again. So if we were to carry this on, I can see that when it gets to u99, that's got an odd subscript here. When we have odd subscripts, u1, u3 and so on, you can see we get 2/3. So u99 is going to be 2/3. And that means that u100 has to be 1 divided by 2/3, 3/2 again. Now I've got 100 terms here, but this pattern of 2/3 plus 3 over 2, if I was just to put that in brackets, that pattern there must occur half the number of terms. So in other words, 50 times. So what we've got here then is just simply 50 lots of 2/3 plus 3 over 2. And whether you do this on a calculator or in your head, it's up to you. If I was to just take this and turn both fractions into sixths, I've got 2/3 is going to be 4/6, and 3 over 2, that's going to be 9/6. So what I've got here then is 50 lots of a total of 13 over 6. And if you do that, you'll find you get the exact value, which we're asked for, of 325 over 3, 325 thirds. Okay, so hope you've been able to see your way through that one. So for this question then, we're given this equation and asked to use Newton-Raphson's procedure to get this iterative equation. So you should be familiar with the Newton-Raphson formula. I'll just give you it here. Okay, so what I'm going to do is just let f of x be equal to the left hand side here. Okay, so if we just put that in, let f of x equal 2x cubed, then plus x squared minus 1. And we need to get the first differential of f of x. So therefore, if I differentiate f of x with respect to x in the usual way, for this term, you're going to get 3 times 2, which is 6. Reduce the power by 1 and you get 6x squared. Differentiate x squared, you get plus 2x. Differentiate the constant on the end, it's 0. Okay? So what we need to do now is just substitute our values into the Newton-Raphson formula. So for the n plus 1th approximation to the root, okay, x, we've got x with the subscript n, and then it's minus, and then we've got our fraction here where we've got f of xn. So I just need to substitute x subscript n into here, and that's going to give me 2x cubed with an n there plus x squared, and again with subscript n there, minus 1. And it's all over that first differential. So just copy this result in. So we've got 6x squared with a subscript n plus 2x with subscript n. Okay? Now, in order to get this fraction, I can see it's all over just one lowest common multiple. So that lowest common multiple here has to be the denominator here. So I'm just going to draw a long line there, and we'll put that denominator in, 6x squared with the subscript n plus 2x with the subscript n. So when it comes to this term, all I need to do is times it by the denominator here. So we've got again 6x squared with subscript n plus 2x with the subscript n. And then we have minus, and then I'm just going to put in brackets there, copy out what we've got up the top here. 2x cubed n plus x squared n minus 1. Okay, just make that a bit longer there. And now all I need to do is expand our brackets and group up terms. You can see here we've got 6x cubed with a subscript n minus the 2x cubed there. So that's going to leave me with 4x cubed with the subscript n. And then here we've got 2x squared, okay, minus the x squared here. And that's going to leave me with plus 1 lot of x squared with the subscript n. And then you've got the minus 1, which is plus 1, and it's all over then that denominator of 6x squared with the subscript there plus 2x with the subscript there. Okay, and that's how we do it. Okay, so a very straightforward part to this question where we've got our iterative equation and we're given that the first approximation to our root x, x1, is 1. And we've got to find out the second approximation and the third approximation. So to get the second approximation, x2, all we need to do is substitute 1 in for x1, okay, into here. So if you do that, you should find you get this result here. Okay, you can see I've substituted 1 in to our equation. We end up with 6/8, which reduces to 3/4. And now to get x3, all I've got to do is substitute 3/4 into our iterative equation, and that will get us x3. So doing that, you end up with a total of 2/3. Okay? So for this last part of the question then, we were given this equation, 2x cubed plus x squared minus 1 equals 0, asked to use the Newton-Raphson method to create this iterative formula where we had the various functions f of x subscript n and the first differential f dash of x of n, and we substituted these into our formula and we derived this. Now we're being asked why we can't take our first approximation x1 equal to 0. Well, it seems as if you were to put 0 in the denominator here, obviously this would be undefined, but this is not going to be sufficient really for this question. What it is that if you put 0 into the denominator, which is basically f dash, the first differential of f of x basically, then what we've got here is the gradient of the tangent comes out at 0. And for the Newton-Raphson method to work, it's based on tangents to the curve crossing the x-axis. So this tangent here would be parallel to the x-axis, it wouldn't cross it, so it wouldn't lead to another approximation. So this would be my explanation. When x1, our first approximation, equals 0, we would have that f dash 0 equals 0, a stationary point, and so the tangent to the curve would not cross the x-axis. Now, if this is a bit confusing, I'll just explain with a graph here. If we were to take the graph of the equation and say it was y equals 2x cubed plus x squared minus 1, that root where it equals 0 is at this point here. And you remember we took our first approximation x1 as being at 1. So we're looking at the tangent at this point here. And if we draw that tangent in, you can see it crosses at this point here. This would be our second approximation to the root. We called it x2, and x2 turned out to be 3/4. And what we do next is we take our value of 3/4 and we're looking at this point on the curve just above it, okay? And we're looking to draw the tangent at that point on the curve. If you did that, it would look something like this. And it crosses the x-axis very close to where the real root is. We found out that that was our third approximation, 2/3. And so you can see it's closing in on the root. So can you see that if we were to take our first approximation where x1 was equal to 0, okay, what we'd be doing is looking at the tangent at this point, and that tangent would be horizontal to the curve, something like that. And so you can see it doesn't intersect the x-axis, so it will give us no second approximation. So that's why we can't have x1 equal to 0. So I hope the graph here gives you some idea why that's so. Okay? Okay, so for this question then, we're given f of x and asked to first of all calculate f of 2 and then express f of x as a product of two algebraic factors. Well, finding f of 2 is dead easy. All we need to do is just substitute x as 2. And if you do that, then what happens is you get this expression, and working out the value of each of the terms comes out to be 0. Kind of expected that because it leads us nicely into the next part, because by the factor theorem, if you've got a particular value of x, in this case 2, that makes it equal 0, that tells us that x minus 2 must be a factor. If you're unsure of the factor theorem, do go back and check that idea out. So for part 2, we know that x minus 2 must now be a factor of f of x. So we can start to build this up, and I'll show you two methods in this of working out that second factor. We've got f of x must be identical then to x minus 2, and it's going to be multiplied now by another factor which has to be a quadratic expression. So the first term in the quadratic expression is going to be an x squared term. Next term would be something x, and then we'll have a constant on the end. So we've got to get minus 3x cubed. And the only term that's going to give us that is when we multiply the x here with the x squared. So clearly it must be minus 3x squared there. X times the minus 3x squared gives me the minus 3x cubed. The term that's going to be a little bit more awkward, but still not that much awkward, is going to be the x term. So I'm going to call it plus bx, okay? And clearly, if we're to get an x squared term, 8x squared here, we get that when we multiply the x with the plus bx. That's going to give us bx squared, all right? We're also going to get an x squared term when we multiply the minus 2 with the minus 3x squared. So that's going to give us plus 6x squared. And we know that the result should really be plus 8x squared. This has got to come to 8x squared. So just by looking at this, we can see that b must be equal to 2. 2x squared plus 6x squared gives us the 8x squared. So I know that for this part then, let's just put underneath. Okay, we've got x minus 2 multiplied with minus 3x squared, and we've got plus 2x so far. And for this quadratic factor, it's got to be a constant on the end. And the only way that you get a constant on the end is when you multiply the minus 2 with the constant that you're going to put here. And minus 2 times something has got to give us the plus 10. It's got to be minus 5. Okay, so we'll put minus 5 in there. And there we have it, okay, our product of two factors. Now, I did say that there was another way that we could do this. I'll just border this off, by the way. The other way is to do algebraic long division. You might prefer that. We know that if we were to divide x minus 2 into, okay, our cubic expression here, let's just copy it down, minus 3x cubed plus 8x squared minus 9x plus that 10, we should end up with our quadratic factor. So I'm going to do algebraic long division. If you're unsure of this, do check out the tutorials on that. So what we do, we say, what do we multiply x by to get minus 3x cubed? And it has to be minus 3x squared. And we multiply minus 3x squared with the x minus 2, put our answer down here, so we get minus 3x cubed. And then minus 3x squared times the minus 2 is going to give me plus 6x squared. Okay, we now subtract just to work out what our remainder is. These two terms cancel one another out, but we have here 8x squared minus plus 6x squared, so that's going to give me 2x squared. So put that down there. And we bring down the next term, the minus 9x. So if I bring that down, we've got minus 9x there. And we start over again. What do we multiply the x minus 2 by to give us that 2x squared? Well, it's got to be plus 2x. So put plus 2x there. 2x times x minus 2 gives us 2x squared, making these two terms the same. And then we get 2x times the minus 2, which is minus 4x. Subtract again just to work out what our remainder is. These terms then cancel. And so what we've got is minus 9x minus 4x. So that becomes minus 9x plus 4x, which is minus 5x. We now bring down the next term, our last term here, that constant, plus 10. And we find that, what do we multiply x minus 2 by to give us minus 5x plus 10? Well, it's got to be minus 5. So we put that up there. Check it out. Minus 5 times x minus 2 gives me minus 5x plus 10. So that when I do subtract, what do I get? I get 0, no remainder. All right, so you can see that minus 3x squared plus 2x minus 5 is our quadratic factor. So you can tackle this two ways, either by just directly working it out like this, as I did here, or you could just do algebraic long division. Okay, so let's give you an idea if that caused any problems. Now for this part of the question then, we're told to show that this equation has exactly two real solutions using A part 2. Well, in A part 2, we found that we had this equation, which is very similar to what we've got here. Do you notice it's exactly the same if I was to let x equal y squared? So when I'm looking at this, remember we factorized this equation and it gave us this result here. So that means that if I was to let x equal y squared, we've got our equation above here, as we see. I can factorize it. Where if I see an x here, just replace it with y squared. So we end up with this result. So it's just a question now of solving this equation. So that means we can put each of these factors equal to 0. So taking this equation here, if I add 2 to both sides and then take the square root, you end up with y equaling plus or minus root 2. So what we have here are two real solutions. So that seems to suggest then that if we've got to show that the equation up here has exactly two real solutions, I would expect this equation to have no solutions. Well, if we look at it closely, we can see that it's a quadratic equation in y squared. We've got the y squared here, and if we square it, we're going to get the y to the power 4 there. All right? So being a quadratic in y squared, if it's to have no solution, I would expect the discriminant, that is b squared minus 4ac, to be a negative number. If you're unsure about discriminants, do check out my tutorials on that. So we have the a in the quadratic is minus 3, the b is the 2, and the c is the minus 5. So using b squared minus 4ac, what we get is the b squared minus 4 times a times c there. Work this out. You've got 4 minus 60, which is going to give you minus 56, and it is a negative number, so we'd expect no real solution. So as you can see, there's only two real solutions coming from this part of the equation. Y equals plus or minus root 2. Okay? Now for this last part of the question then, we've got to deduce the number of real solutions for this equation here, where theta is greater than or equal to 7 pi but less than 10 pi. So from the first part, or an earlier part, okay, we had this equation here and we found out that there was only one solution to it. That was because there was that factor x minus 2 equals 0 leads to x equals 2. The other factor, the quadratic factor, the discriminant was less than 0, so there was no solution. So all I need to do now, when I look at comparing these two equations, you can see that x is being replaced with tan theta. So what I've got here then is, if we let tan theta be that x, then tan theta must be equal to 2. So we just need to find out how many solutions this equation has in this range here. And to do it, all I need to do, or the way I'm going to do it anyway, is draw a quadrant diagram. I think you'll find this is the quickest way. I'm assuming you're familiar then with quadrant diagrams. Again, if not, do check out my tutorials on this. So I've taken 0 degrees or 0 radians. Okay, we're going to be working in radians and we're looking for positive values of theta. So that's turning in an anti-clockwise sense. And tangent is positive because we've got positive 2 there in the first quadrant. That's that one there. Okay, so draw a line inclined to the horizontal here. And it's also positive in the third quadrant. Okay, so you should have another line down here equally inclined. Okay, these two angles should be exactly the same. So the solutions that we would want would be ones that start from here, turn in an anti-clockwise sense to the blue lines that you see here. So there'll be one solution here, starting back here again, there'll be another one there, going back again, there'll be another one all the way round to there, and so on. Keep turning round till we hit a blue line. The thing is, we want to know how many solutions are in this range. So let's just have a look at what we could have. So we've got this quadrant, so that's going to be between 0 and this one over here, which would be pi radians if we were to turn half a turn. If I was to start again, go all the way around here, I'd pass pi radians, and this would be between, or it'd be more than pi, but less than 2 pi. So that's what we would have over there. If I was to start again, go all the way around here, back to this one, then this is between 2 pi and the one over here, 3 pi. Now if I was to keep this up, on this side I've got all the even multiples of pi. So in other words, you've got 4 pi, 6 pi, 8 pi and 10 pi. Whilst on this side you've got all the odd multiples of pi. So working back, we've got from 3 pi, we've got 5 pi, and we've got 7 pi, and we've got 9 pi. So how many solutions am I going to have then in this range? Well, starting from here, I'm going to keep going round and round until I get into ranges like this, okay? Now, if I keep going round and round, I've got to pass the 6 pi, I'm going to go past the 7 pi, and I'm going to be just greater than 7 pi when I'm on this side here. So I'm going to keep going round and round and round, okay? I can't draw all the times I keep going round, but hopefully you can imagine it, okay? And my first solution lands on this one. It's greater than 7 pi, but less than the 8 pi here. I carry on round, get to this one, and I'm greater than 8 pi, but still less than 10 pi. So that's going to be my second solution. Carrying on round here again, I'm going to pass the 9 pi now, but still be less than 10 pi. So I'm going to land on this one here, and there'll be another solution there, my third solution. Okay, so once I carry on beyond here, I'm going to be going to this one, but I'm going to pass the 10 pi, okay? So can you see then that there's going to be a total of 3 solutions? The one that exceeds the 7 pi, the one that exceeds the 8 pi, and the one that exceeds 9 pi. 3 solutions. So therefore we have 3 solutions in that range. So I hope that method's been clear for you. It's the method that I prefer. I'm sure there's a graphical method out there that you could use, but I think that's going to take longer. Okay, so that's just in my opinion. Okay, so for this question then, we've got to solve this trigonometric equation. 4 sine x equals sec x. And x is measured in radians. We've got to give it in this range here, where it's greater than or equal to 0, but less than pi upon 2 radians. So what would we do? Well, I'm going to take that equation and we've got to get it into the same trigonometric function. So I'm going to change sec x to 1 over cosine x. Okay, you should be familiar with that result. And then going to multiply both sides by cosine x. That's going to lead to 4 sine x cosine x equals 1. And then I can see that the identity 2 sine x cosine x is basically in here. You should remember that 2 sine x cosine x is the same as sine 2x. So by changing this to 2 multiplied by 2 sine x cosine x equals 1, I can now pick up on that idea that this is sine 2x. All right, so if we do that, we now achieve our one trigonometric function, sine 2x. And so I can divide both sides by 2, giving me sine 2x equals a half. And to get 2x, I just need to take the inverse sine of both sides, leading to 2x equaling the inverse sine of a half. And this should be very recognizable, certainly in degrees, as being 30 degrees. But we've got to work in radians, so therefore 2x would be the equivalent of 30 degrees in radians. That would be pi upon 6. Okay, pi upon 6 radians. Now at this point, I'd want to try and figure out what the other answers are by drawing a quadrant diagram. Okay, so we'll just put our quadrant diagram in here. This will be 0 radians. The equivalent to 90 degrees would be pi upon 2 radians. But we're doubling our value for x here. So if I was to double the values of x, we've got a new range. I'll just put this in here. A new range which is going to be doubling all of these values here. Doubling 0 is 0, but doubling x becomes 2x, and doubling pi upon 2 becomes pi. Now we know that sine is positive in the first quadrant and the second quadrant. So if I was to draw two lines equally inclined then to this horizontal line, marking those angles in the usual way, then we're looking at two answers in this range for 2x. The first one is going to be this one here. This is a possible 2x. And the other one, starting from here, going anti-clockwise, passes the pi upon 2 there and goes to there. This is a 2x, okay, which is less than pi radians. Remember, pi radians would be to this part here. So we have got that 2x equals pi upon 6. I'll just mark it in here again. 2x equals pi upon 6. That's one solution. That's that red one. And as for the green one, well, that's going to be pi radians, right the way round to there, minus this angle in here, which I failed to put in, okay, is the pi upon 6. So we've got pi radians minus the pi upon 6. If you do that, you should find you get 5 pi upon 6 radians. And that's the green value for 2x, okay? Now, all I need to do is divide both sides by 2 to get x. Halving pi upon 6 is pi upon 12, and halving 5 pi upon 6 is 5 pi upon 12. Okay, radians. And there's our two solutions. Now, in this question, we're asked to solve this trigonometric equation, 5 sine theta minus 5 cosine theta equals 2 in this range. And there's several ways that we can do this. I often find that students want to square both sides of the equation. Yes, you can do this, and I've done it in another video. It's not a method though that is easy. You've got to take care with solutions. No, the method that I prefer to use is this method where we take this harmonic formula and rewrite this expression in this form, r sine of theta minus alpha. This equation has this particular form. If you're unsure of this, do go back and check out tutorials on harmonic formula on my website, okay? It's a very quick, easy method once you get used to it. So what we've got here then is 5 sine theta minus 5 cosine theta. It's got this form here. If we were to write that in, you can see that it's identical in form to a sine theta minus b cosine theta, where a is 5 and b is 5. And we can see that the r is the result of square rooting a squared plus b squared. So if you were to do that, r is the result of square rooting 5 squared plus 5 squared. Well, that's going to be 25 times 2, root 50, but keeping it in this form, you can split it up using the laws of surds. The square root of 25 is 5, and we'll just do the root of 2, just leave it as root 2. So that's our value for r, and alpha is the inverse tan of b over a, so that's going to be the inverse tan of 5 over 5, which leads to the inverse tan of 1, which is 45 degrees. So that means that we can express our equation here using this result, r sine of theta minus alpha. We can express it as 5 root 2 sine of theta minus 45 degrees, and that equals 2. So all we need to do now is divide both sides by 5 root 2. If you do that, you're left with theta minus 45 degrees equals the inverse sine of 2 all over 5 root 2. And at this point, if we take the inverse sine of 2 over 5 root 2, you get that theta minus 45 degrees is equal to 16.429 and so on degrees. And with this, to get other solutions, I'd want to sketch a quadrant diagram. Should be familiar with quadrant diagrams. If not, do check out my tutorials on this. We've got our 4 quadrants starting at 0 degrees, 90, 180, 270, back to 360 degrees if we move in an anti-clockwise sense. Sine is always positive in the first and second quadrants, and we draw 2 lines then in the first 2 quadrants equally inclined to the horizontal here. Okay, so I'll do one there and one there. Okay, so those 2 angles are meant to be the same. And when we did the inverse sine of theta minus 45 degrees, we got 16.429. So that's going to be this angle in here. It's not drawn to scale, but hopefully it just gives us an idea of what's going on. So we want one of those angles. This is one of them. This is our first one in the range 0 to 360 degrees, which is a possible value for theta minus 45 degrees. When it comes to our second solution, it's going to be from here, going round here, anti-clockwise to this line. This is another possible theta minus 45 degrees. Okay, so this one here is our red one, and to get the green one here, all I've got to do is 180 degrees minus the 16.429 degrees. If you do that, you should find you get 163.570 and so on degrees. That's our green one, okay, for theta minus 45 degrees. So it's just a question of adding 45 degrees to both of these answers. If you do that, you'll get these 2 results here. And then I just need to round these up to 1 decimal place. And if you do that, you end up with our two answers, theta being 61.4 degrees and 208.6 degrees, both to one decimal place then. Okay, so I prefer this method compared to a squaring method. As I say, you can check that out in the other video that I've done that accompanies this one. Okay, if you're on my website, you should see it. Okay, so there we go. Hope you've been able to follow that. So we've got to solve this equation then, 5 sine theta minus 5 cosine theta equals 2 in this given range for theta. Now there's several ways that you can do this equation, and one of the most popular ways, not that I would encourage it, okay, is to use the squaring method to basically square both sides of this equation. Why don't I like it? Well, you've got to be very, very careful towards the end, because you could find yourself writing down invalid values for theta, as I'll show you. So let's just take this method where we're going to basically square both sides. So you could put brackets around all the left hand side and square that out, and it equals 2 squared, in other words 4. Basically though, I'm going to just pull out 5 as a common factor. I think it's a bit easier to work with, but you can make up your own mind on that one. So I've pulled out 5 as a common factor here. And then you could again square it from this point if you like, but I'm going to divide both sides by 5. If you divide both sides by 5, you're going to get this result. Now I'm going to square both sides. So squaring the left-hand side gives me just sine theta minus cos theta all squared, and squaring the 2/5 gives me 4/25. So I'm now going to square this bracket out in the usual way. We're going to get sine squared theta minus twice the product of these two terms. That'll be minus 2 sine theta cos theta, and then the last term squared. That's going to be plus cos squared theta. So we've got this particular equation. Now we should pick up on a couple of identities. You should be familiar with the identity sine squared theta plus cosine squared theta. That's identical to 1. And also this 2 sine theta, cosine theta, should recognise that as being sine 2 theta. I'll put them in here just as a reminder. Okay, so that means that I could take 4/25 from both sides, and I'll add what is effectively here sine 2 theta to both sides. So if you do that, you're going to get this result here. Okay, remember that one came from sine squared theta plus cos squared theta. Now if you work out 1 minus 4/25, you're going to get 21/25, and that's going to be equal to sine 2 theta. So to get 2 theta, I just take the inverse sine of 21/25. And if you do this on your calculator, remember you should be working in degrees mode, so make sure your calculator's in degrees mode. If you do that, the result that you'll get for 2 theta will be 57.140 and so on degrees. Now it's from here on that we've got to take a lot of care. So what I'm going to do is just remove those identities there. And this is the reason why I'm not wild about this particular method. If we were to look at this equation here and work backwards, if we were to square root both sides, sine theta minus cosine theta could equal plus or minus 2/5. But we've seen that it's a positive value only. If it was a negative value, it would mean that sine theta minus cosine theta would be a negative value. Sine theta would be less than cosine theta. But for it to be a positive value, we need results where sine theta is greater than cosine theta. So our values of theta are going to be limited. Just to show you further, if we were to take the graphs of y equals cosine theta, illustrated in red here, and y equals sine theta, okay, you'll notice that they intersect at 45 degrees and 225 degrees between 0 and 360 degrees. And sine theta is greater than cosine theta between 45 degrees and 225 degrees. I've got it summarized here. And this would lead to positive results in this bracket here. So I'm looking at 2 theta. So if I was to double this range here, doubling the 45 is 90 degrees, doubling theta is 2 theta, and doubling the 225 degrees is 450 degrees. So I'm looking at a range for 2 theta between 90 degrees and 450 degrees. Now if we draw a quadrant diagram, we're looking for where sine is a positive value. And we should be familiar with this, that sine is a positive value in the first quadrant and the second quadrant. So in the usual way, we'll draw 2 lines equally inclined to the horizontal. We'll mark those angles in as being exactly the same, and they will be that 57.140 and so on degrees. Now when it comes to working out what 2 theta is, we need to find our solutions in this range. So for 2 theta being greater than 90 degrees, the first one, starting from here, has got to turn beyond this line here. There's our 90 degrees, so it's going to be the first one's going to occur when we turn to this blue line here. So starting from there, we're going to go all the way round, like so, until we hit that line. That's a possible 2 theta, greater than 90 degrees. Now where's the next one going to come from? Well, starting from here again, we've got to turn all the way round, okay, beyond the 360 degrees to this next one. We should realize that 360 degrees plus a further 90 degrees is our 450 degrees up here. So we need a solution that goes from here all the way round, okay, like so, right the way around past the 360 degrees up to this blue line here. And that's a possible 2 theta, which is less than the 450 degrees, which would take us up to here, this line here. So we don't need to go round anymore, not to this blue line here. We've just got these 2 solutions for 2 theta. So what are those values? Well, from that point of view, we therefore have that 2 theta must be equal to, well, for the red one, it's going to be 180 degrees minus the 57.140 degrees, and that's going to be 122.85 and so on degrees. And I'll just mark that in as the red one. And for the green one, well, that's going to be 360 degrees plus another 57.140 degrees. And that's going to give us 417.14 and so on degrees. And just mark that in as our green version for 2 theta. So if you were to divide both of these answers by 2 now and round up to 1 decimal place, you're going to get 61.4 degrees for one of them. And if I divide this one by 2, you're going to get 208.6 degrees. Okay, and both of these are to 1 decimal place, 1 dp for short. Okay, so as you can see, this is quite a tricky way of doing this equation, not a method that I would really encourage, purely because we've got this complication that because we squared our equation, we are getting the possibility of having solutions which would have led to this bracket, sine theta minus cosine theta, being a negative value. All right, which is not the case. It has to be a positive value leading to our result here of a positive 2. Okay? Okay, so for this question then, I've sketched the trajectory of the rugby ball and we're told that it has a maximum distance of 40 meters. So when it's kicked from here, and so it's going to pass through the point 40, 0, and it reaches a maximum height of 12 meters. Well, that means that because this is modeled as a quadratic curve, then this point up here must have coordinates on that line of symmetry. So it's going to have a coordinates 20 and then 12. So we've got to get the equation of this trajectory. And one way that you could do this is to say, well, okay, we know that when h equals 0, x will either equal 0 or 40. And so that means that we could either have x as a factor or x minus 40 or even 40 minus x. I'm going to go for 40 minus x, knowing that this is a negative quadratic, and you can see that you're going to get x times minus x here, which is going to be minus x squared. You don't have to do that. You could have this as h equals, and you've got when h is 0, you know that x could equal 0, or you've got the other factor which could be equal to 40 as x minus 40. It's up to you. The thing is, don't leave it in these two forms, okay? It's got to pass through 2012, and so we're going to need a constant to enable that to happen. So I'm going to stick a constant in here, call it a. I could use the same constant here, although it won't be the same value as this a. I'm going to change it to another constant, let's say b. But whatever this constant a is, b will be the negative of it. Okay, I'll just put it down here, that the constant b will equal minus a. Okay, let's just work with this one here. Now, we've got to establish what that constant a is. And so it's easily done because all we need to do is just substitute when x equals 20. We know that maximum height h equals 12. And if you do that, let's say we substitute it in here, then we therefore have that 12 equals a times 20. I'll just write it as 20a times 40 minus the 20, which is going to be 20. So we've got 400a on the right hand side here, so a must be equal to 12 divided by 400. And I would cancel top and bottom here by 4, and that will just give me 3 over 100. So what we end up with for the equation for h, or one possible equation, is h equals 300th x times 40 minus x. Or if you did this version, you would have h equals minus 3 over 100 times x minus 40. Check it out, okay, if you're unsure how I got that. Okay, just by substituting these values in, you'll find that the constant b is minus 300ths. Okay, so I was giving you an idea anyway on one way of doing that question. Now we're told that the rugby ball passes through a point that is 3 meters above the ground, and we've got to find the furthest distance that is away from where the ball was kicked. Well, it's got to be on this branch of the curve, and let's say it's this point here. Its coordinates then will be, let's say, x and then 3, okay? x3. So we've got to establish the value of x, and it's just going to be a case of substituting h equals 3 into this equation and solving it for x. So if we're to do that, we just got that when h equals 3, then substituting that in gives us 3 equals 3 over 100 times x times all of 40 minus x. And if I was to divide both sides by 3, I can see that those two 3's would cancel out. And then it's just a question of multiplying now through by 100 and expanding the bracket. You're just going to get 100 then equals 40x minus x squared. And this is a quadratic equation, so just rearrange it into the form x squared minus 40x and then plus 100 equals 0. And we can solve this by either using the quadratic formula, or better still, since this is very straightforward, I'm going to use completing the square. And if I complete the square, I've got a bracket here, all squared, just halve the minus 40x, so that becomes minus 20. And if you were to square this out, you'd get x squared. You'd get twice the product, that'd be minus the 40x, and you'll get the minus 20 all squared, which would be 400. So we just need to take 300 away from that in order for 400 minus 300 to give us that 100, and that equals 0. So all I need to do now is just add the 300 to both sides. That's going to leave me with x minus 20 all squared, and that's going to equal 300. And then if I take the square root of both sides, I end up with x minus 20 equaling square root of 300. Remember, it'd be plus or minus, so we'll put that in there, and then just add the 20 to both sides. So x equals 20 plus or minus the square root of 300. You'd arrive at this result if you use the quadratic formula. Okay, we want the maximum distance that x could be. So for the maximum distance x could be, it's got to be the positive value there, 20 plus the root of 300. If you took the negative value, it's going to give you the distance x here, where you've got 3 meters high for that pole if it was placed in this position up here. Okay, but we want that maximum distance, so it's got to be on this branch. Well, if you work this out on your calculator, you're going to get 37.32 and so on. Round that up to say 3 significant figures and you've got 37.3. Units are meters, and the accuracy then that I've used here is 3 significant figures, 3SF for short. Okay? So for this last part of the question, we're being told to give one limitation of the model. Well, looking at the mark scheme, they've given several examples, and hopefully you would have had one of these ones. We are assuming that the ground is horizontal. Very unlikely. There's going to be some bumps, I'm sure, in the ground. Okay, so not necessarily going to be horizontal. The ball needs to be kicked from the ground. Well, it might not be. Okay, it's going to be maybe bouncing just before it's kicked, say. The ball is modelled as a particle. Ball is not a particle really. Okay, it's got a diameter. A particle will be infinitesimally small. Okay, the diameter would be negligible, shall we say. The horizontal bar needs to be modelled as a line. Well, that's possibly going to dip in places. Okay, so we are assuming that it's horizontal. There's no wind or air resistance on the ball. If there were, then that's going to distort the path. Okay, it wouldn't necessarily be a quadratic, follow a quadratic curve. And there's no spin on the ball. That's going to be very unlikely. If there was spin on the ball, that could also cause resistance and alter the path's trajectory. No obstacles in the trajectory or path of the ball. Obviously, if somebody gets in the way, then that path, that trajectory, isn't going to be completed. And the trajectory of the ball is a perfect parabola. Well, as I said in some of these other questions, it's not necessarily going to be a perfect parabola, especially if there's wind or air resistance on the ball. Okay, so just a few of the limitations to this model, and if you can give one of those, okay, then sure you'll get a mark. Hi there. Now in this video what I want to do is show you how you can differentiate from first principles y equals cosine theta and get the result that dy by d theta is equal to minus sine theta. And what I'm going to be using are these two results that you see here that I'm taking as assumed knowledge. So what we do is we increase the angle theta by a small amount, let's say delta theta, and what we get now is the cosine of theta plus delta theta, and this is going to result in a small increase in y, which I'm going to call delta y. So we end up with y plus delta y equals the cosine of all of theta plus delta theta. Next I'm going to subtract y from both sides, so therefore I get delta y equals the cosine then of theta plus delta theta and then minus the y. And I'm going to now expand the cosine of theta plus delta theta using this identity here, which, as I say, you should be familiar with. And what we end up with is delta y equaling the cosine of theta times the cosine of delta theta minus the sine of theta sine of delta theta, where I'm just replacing the a with theta and the b with delta theta. Okay, so we end up with the cosine of theta, cosine of delta theta minus the sine of theta sine delta theta, and then we've got the minus y here, which I replace now with cosine of theta. Now the next thing I do is just factorize the first term here and the last term here. I can see that cosine theta is a common factor, so I have delta y equals, and pulling out the cosine of theta as a common factor, I have the cosine of delta theta and then minus 1 here. And then we've got this second term there, minus sine theta sine delta theta. And the next thing I do is I divide both sides by delta theta. I'll do it on the same line here, okay? So that's delta y over delta theta equals all of this term over delta theta, but I'm just going to put this factor here over delta theta. It's exactly the same as putting it all over delta theta. And I need to divide this term by delta theta, but I'm only going to put this part over the delta theta. Why did I do that? Well, I'm going to be picking up on this result here, because what I'm going to do is let delta theta tend to 0. So let's just write that in here. As delta theta tends to 0, then delta y over delta theta is going to tend to a limit, which that limit is going to be dy by d theta. So delta y over delta theta tends to a limit which we call dy by d theta. And this has got as h tends to 0. Well, I'm going to replace the h by delta theta. And as I say, we should be familiar with these results. If not, we'll just assume that they're correct. And so that would lead to sine of delta theta over delta theta tending to 1. So this term here would tend to 1, and the cosine of delta theta minus 1 over delta theta would tend to 0. That's that part there. So putting those results down, we can see then that dy by d theta, let's put dy by d theta, is going to equal, well, for this part it's going to be cosine theta multiplied by 0, that's going to be 0, and then here we just end up with minus sine theta multiplied with 1, so that's going to give minus sine theta, and that's differentiating cosine theta from first principles, giving us dy by d theta is minus sine theta. Okay, so I hope you're able to understand that, and thanks for watching. So for this question then, what I've done is just drawn a sketch of our suite. Initially it has a diameter of 5 millimeters, and then we're told that after 4 minutes its radius is now down to 3 millimeters. We're also told that the rate of decrease of the radius is inversely proportional to the square of the radius. And we're being asked to find an equation relating the radius to the time. And we must define the units that we use. Well, first of all, what I'm going to do is define the units. And by that, I'm going to let r be the radius in millimeters and let t be the time in minutes. So if we're to build an equation up, we start with this statement here: the rate of decrease of the radius is inversely proportional to the square of the radius. And I can write that as this differential equation. We've got dr by dt, that's the rate of change of the radius, okay, with respect to time. And it's going to be inversely proportional then to the square of the radius. So that means that we can call in a constant, which I'm going to call k, and being inversely proportional to the square of the radius, that's going to be divided by r squared. Now I could leave it as an equation like this, but I would prefer, because it's rate of decrease rather than increase, to put a negative sign here, because I would expect that to be a negative value, and that would mean that that constant k would be a value that is greater than 0. Now you could use this result, dr by dt, the rate of change of the radius with respect to time, is equal to k over r squared. But if you did this version, you would expect k to come out as a negative constant, okay? And you might want to try this version. This k here will be the negative of the k that I find in this solution. Okay, so it's up to you, but this is the version that I would prefer. Okay, so in order to solve this, we've got to separate the variables. By that, we need to put the r's on one side and the t's on the other. So if I rearrange this, I could multiply both sides by r squared, and I'm going to get r squared dr, and I'm going to remove the dt. It's as if I'm multiplying by both sides by dt, and that's going to give me the minus k and the dt. And I'm going to integrate both sides. So I integrate that side, and I could slip an integral out the front here, but this being a constant, it's better really to put the integral after the constant here. Okay, now if we integrate this left hand side with respect to r, just add 1 to the power, that's r to the power 3, and divide by the power. Okay, simple integration there. And if I integrate minus k with respect to t, I'm just going to get minus kt. So we get that is equal to minus kt. And I've got to add a constant. Now, it doesn't matter which side I add the constant to. I'm going to just add it on the right-hand side. Call it plus c. Okay? And I'm going to call that equation 1. We're going to come back to that equation in a few moments. Because what I've got to do next is work out what this constant is. And I can easily do that by looking at this initial condition. I know that at the start the radius was 5 millimeters. So in other words, that's when t is equal to 0. When t is equal to 0, r is equal to 5. And what I can do now is just substitute those values into equation 1. So I'm just going to put up here sub in 1. All right, and if we do that, what we're going to get is r cubed. Well, that's going to be 5 cubed. That's going to be 125 then over 3. So we therefore got 125 over 3. Knowing that t equals 0, this term goes out, and that just leaves me with the constant c. Okay? Now I need to work out what k is. And I can easily do that now just by using this other condition. And that is that when t equals 4, we know that the radius r equals 3. And so if I again substitute these values back into equation 1, just put a note there, then what I get is that radius 3, when you cube it, that's going to be 3 cubed at 27. Divide by 3, that's going to give me 9. And that's going to equal minus t, which is 4 times the k. So minus 4k. And we've got the constant c, which we've just found out was 125 over 3. And so I can easily rearrange this. If I add 4k to both sides, I'm going to get 4k, and take 9 from both sides. 9 is 27 thirds, so 125 thirds minus 27 thirds. That's going to leave me with 98 thirds. And so therefore, if we just carry on down here, we're going to get that k, if we divide both sides by 4, k equals 49 over 6. And so all I've got to do now is just substitute this value of k back into 1. Okay. And if I do that, I'm going to get r cubed over 3 is equal to minus kt. We know that k is the 49 over 6, so it's minus 49 over 6 times t plus the constant c, which was 125 thirds. And there's an equation that relates the radius r to the time t. Okay? Okay, for this part of the question then, we've got our equation that relates the radius of the sweep in millimeters, r, to the time t given in minutes. And we're being asked then to find the time it takes in minutes and seconds to the nearest second for the time it takes for the sweep to dissolve. Well, that's going to be when the radius is equal to 0. So all we've got to do is let r equal 0 and work out the value of t. So if you were to do that, that is to let r equal 0, substitute it into the equation, you're going to get this result here. Then what I want to do is just add 49/6t to both sides, and that will give me this equation. Next, I want to times both sides by 6 and divide by 49, and that will give me t. T will equal 125 thirds then multiplied by 6/49. If you work that out on your calculator, you'll end up with t equaling 250 over 49, or as a decimal 5.1020, and so on. And remember, that's given in minutes. Now we're being asked to give this to the nearest second. So we know we've got 5 minutes. It's just a question of converting 0.1020 and so on to seconds. So I've just got to, well, I could take the 5 off if you've got this displayed on your calculator. That will leave me with 0.1020 and so on, and multiply that result by 60. If you do that, you should end up with 6.122 and so on. So we know then that we've got the time taken is 5 minutes and 6.122 and so on seconds for that sweet to dissolve. And so if you round that up to the nearest second, then it's going to be 5 minutes 6 seconds. Now for this last part of the question, they're asking us to suggest a suitable limitation of the model. And I've got examples down here. In fact, these examples are not my ideas. These are the examples that they give in the mark scheme. So you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 different examples here. So I'll leave you to just pause the video, and you can have time just to read over what they suggest. Okay? So for this question then, we've got to take this fraction here, express it in partial fractions, finding the constants a, b and c. Well, what we could do is multiply both sides by this denominator here, x minus 3, 1 minus 2x. And if we do that, we're therefore going to have on the left 1 plus 11x minus 6x squared. And when it comes to multiplying the a with this denominator, we're going to get a times x minus 3 multiplied with 1 minus 2x. When it comes to this term here, we're just going to have b multiplied by the 1 minus 2x. So b times the 1 minus 2x. That x minus 3 would cancel out with that x minus 3 there. And for this last term, multiply it with x minus 3, 1 minus 2x, then the 1 minus 2x's would cancel, and you'll just be left with c times the x minus 3. Okay, so all we need to do now is just pick appropriate values for x. And it's good to just make each of these brackets equal to 0. So if we were to take this bracket, make it equal to 0, then x would equal 3. So let's start with that. Let x equal 3. And if we do that, we end up with 3 substituted in here. That will give us 1 plus 33 minus 54. And that leaves me with minus 20. And if we substitute 3 into the right hand side here, this will be 0, so this term goes. This last term will be 0, so that goes. Just putting 3 in here is going to give me 1 minus 6, that's going to be negative 5b. Okay, minus 5b then. And if I divide both sides by minus 5, you can see that b turns out to be 4. So that's good, we've got one value there. Need another value for x, and if I make this bracket equal to 0 by choosing x equals a half, then that's going to make this a lot simpler. So we'll put let x equal a half. You can take any value you like, but you're trying to avoid simultaneous equations, remember. Okay? So by choosing these values here, we can avoid simultaneous equations. By letting x equal a half, substitute it into here, you should find you get 5. And putting a half into here, that term goes to 0. This term goes to 0. So we've just got a half minus 3, which is minus 2.5. Better to write it as a top-heavy fraction, minus 5 over 2. So it's minus 5 over 2, and that be multiplied by c. And I can see now that if I multiply both sides by 2, I'm going to end up with 10 equals minus 5c, and if I divide both sides by minus 5, I end up with c equaling minus 2. Now, as I said earlier, you can use any value of x that you like, and we've now made each of these brackets 0 by choosing these two values here. And I can pick, say, any value of x. I'm just going to choose x equaling 0. So we'll just say let x equal 0. I feel that's going to be a quick, easy value to use, but try it with other values if you like. So if we let x equal 0, then we're left with 1 here. So we've got 1 equals, and put 0 in here, we end up with minus 3 times 1, so that's minus 3, times that a, so that's minus 3a. And 0 in here just gives us b, so it's plus b, and 0 in here gives me minus 3c. And I've already got the values for b and c, so I might as well substitute them in. And putting the value of b in as 4 and c in as minus 2 here, I'm going to get minus 3 times minus 2, which is going to be plus 6. So I've got 10 here, subtract 10 from both sides, or actually I'm going to add 3a to both sides, so I'm going to end up with 3a equals, and I'm going to subtract the 1 from both sides, so 10 minus 1 is 9, and clearly a is going to equal 3. And so there are my three values then for a, b and c. So for this part of the question then, we're asked to show that f of x is a decreasing function. In other words, the gradient would always be negative. So in order to do this, I've got to differentiate f of x and show that that gradient is negative. Well, to differentiate this, it's best if we split this into the partial fractions. Well, we did that in the previous part of the question, and we got this result here. Now, if I'm going to differentiate this, it's best if I rearrange these fractions, bring the denominators up to the top. So this is going to be 4 times all of x minus 3 to the power negative 1, and this will be minus 2 times 1 minus 2x to the minus 1. So I get this result here. Now I'm going to differentiate this. It's ready for differentiating. So therefore we get f dash x, or f prime x, the first differential of f of x. With respect to x, well, when it comes to differentiating 3, that's going to go to 0. When it comes to differentiating this term here, we need to use the chain rule. Essentially, what we're doing then is this. If we're going to use the chain rule, dy dx equals dy dt times dt by dx, we would let y, say, equal 4x minus 3 to the power minus 1, and t would be this x minus 3. So what we end up with is y equals 4t to the power minus 1. 4t to the power minus 1. So differentiating this, you want to do dy by dt first of all, this one here. So thinking of this as 4t to the minus 1, then you're going to get minus 4 times t to the minus 2. T, remember, is the x minus 3, and then that's to the power minus 2. And then we need to multiply it with dt by dx. Differentiate what we called t, which was x minus 3, differentiate that with respect to x. Differential of x minus 3 with respect to x is just going to be 1. So what I'm trying to show you here is how I would do it without really writing this out. That's how I'm thinking about it. So I'll do a similar thing when it comes to this result. I'm thinking of this as minus 2t to the minus 1. So I differentiate minus 2t to the minus 1, and I would get plus 2 times t to the minus 2. And t, remember, is 1 minus 2x, and that be to the power minus 2. And then I need to multiply it by the differential of what I called t. Differential of 1 minus 2x then is negative 2. So just put the negative 2 in there. And when we tidy this up, I've got minus 4x to the minus 3 all to the power minus 2. So it's going to be minus 4 all over x minus 3 squared. And this will be minus 4 all over 1 minus 2x all squared. So that gives me that result there. Now we should be able to see that this is a decreasing function, because in the denominator here you've got a squared value. Same applies over here. So both the denominators here are going to be positive values. So we've got minus 4 over a positive value, so this term here is going to be negative for any value of x. And the same argument holds for this. This is going to be a negative term. So in conclusion then, what we've got is that since each term has a positive denominator, it's squared, then each term here is going to be negative. And so the sum of two negative terms is going to be negative. So therefore, f dash x, that first differential of f of x, is going to be a negative value, less than 0. And so f of x is decreasing. Hi, so for this question then we've got to prove this identity here, and what I would do is start, say, with the left hand side, purely because normally I've got more terms here, a couple of terms, and I've got to get it down to one term. So starting with that, mind you, you can start with the other side, it's up to you. If I was doing it, I would go for the proof. Okay, so we've got proof, and I would copy down 1 minus cos 2 theta and start to think about what this is identical to. Well, you should be familiar with cosine of 2 theta, that identity. There's 3 versions for it, okay, as you can see here. So looking at it, I can see that if I take this middle identity for cos 2 theta, then let's just mark that one up there. I can see that rearranging it, if I add 2 sine squared theta to both sides, okay, what I end up with is 2 sine squared theta is identical to 1, and then I can subtract cos 2 theta from both sides and I get 1 minus cos 2 theta. So straight away I can see from that result there, okay, that 1 minus cos 2 theta here must be identical to 2 sine squared theta. The problem is though, where do I go from here? I've got to get it down to tan theta sine 2 theta, and it doesn't look that easy. So what I might be tempted to do now is just look at the right hand side and see if this gives me any clues. So looking at the right hand side, tan theta sine 2 theta, let's just write that down here, okay, tan theta sine 2 theta. What's that identical to? Well, tan theta is the same as sine theta over cosine theta, And sine 2 theta should know is a basic identity. It's 2 sine theta cosine theta. And I can see that this cosine theta here cancels out with that cosine theta there. And look what I get. I get that this is identical to 2 sine squared theta. So I could work backwards from this and prove that it equals this. But having just worked this side out, I can see that this is very quick, because I could take this result here and just simply write 1 minus cosine of 2 theta. And so this would have served then as the proof. It's a much quicker, better version than what I did up here. But okay, I selected this one. How would I finish it off? Well, all I've got to do is just set this up as this statement here. Sine theta over cosine theta. And just put the 2 sine theta cosine theta in here. And we can see straight away then that this is tan theta and this is sine 2 theta. So in hindsight, starting with 1 minus cosine 2 theta didn't really seem to be the best solution. I would prefer this one now, okay? But there you go. You live with what you try, okay? So hope you've been able to see how I would approach such a problem. Okay, so for this part of the question then, we're asked to solve this equation for x between the values minus pi upon 2 to pi upon 2. Remember, x is measured in radians. And we were given this identity in the previous part of the question, and it said hence, so we're expected to use it. It should help us. So I can see straight away that in this equation here, 1 minus cosine 2x, if we replace the theta with the x, it's going to be the same as tan x sine 2x. So that must be where they want us to pick that identity up. So if you were to substitute that in, there it is there, tan x sine 2x in place of 1 minus cos 2x. Now what I can do next is take 3 tan squared x sine 2x from both sides and factorise. I'll show you. What we get is if we take the tan x sine 2x outside this bracket, then we've got it multiplied with the sec squared x minus 5. Okay, that gives us that term there. And then if I've subtracted this term from both sides, you can see that tan x sine 2x times the minus 3 tan x would give me negative 3 tan squared x sine 2x. All right. Now I can see that sec squared x, I can pick this up as 1 plus tan squared x, a basic identity you should be familiar with. And this would allow this bracket here to form a quadratic in tan x. So I've made that substitution there. And what I'm going to do now is just tidy this bracket up. So if we tidy that up, we're going to end up with that quadratic in tan x here. So I've got 3 factors, tan x, sine 2x, and this bracket that would equal 0. So that leads me to that result. And I can solve each of these 3 equations now. Starting with this first one, tan x equals 0, that's easy because x will equal the inverse tan of 0, and the inverse tan of 0 is simply 0. Okay, nice easy answer there. And when it comes on to sine 2x equaling 0, all I need to do is say that 2x equals the inverse sine of 0. Should know the inverse sine of 0 it is 0, so we get 2x equals 0, and if I divide both sides by 2, x will equal 0. Now, for the quadratic in tan x, I need to factorize this, and it factorizes very easily to tan x plus 1 times tan x minus 4 equals 0. And that would mean that each of these factors would equal 0, leading to tan x equals negative 1 and tan x equals 4. So solving for tan x equals negative 1, x would equal the inverse tan of negative 1, and should be familiar with that one. That's a very standard result. It's in degrees, it would be minus 45 degrees. The equivalent in radians is minus pi upon 4. Okay? Now when it comes to tan x equals 4, that's not so obvious. You're going to need to use your calculator there. Make sure you're in radians mode. Take the inverse tan of 4 and you get x equaling 1.3258 and so on. So now I've got all my results that are in this range. So just to summarize then, x equals minus pi upon 4, 0, and 1.326 radians to 3 decimal places. You could put a little c here if you wished to indicate that those were angles in radians. But it's understood that x would be in radians from here, so it doesn't really matter if you did leave it off. Okay? Okay, so for this question then, we've got to find this area R, bounded by the curve C, the x-axis and the line L. Now if you had a go at this and just want to check out the answer, best to fast forward obviously, because it's a very long solution, and I'm going to take you slowly through the method. And that method is to, first of all, split this area R into two sections. By drawing a line down from P to the x-axis, I'm going to work out the area of this first section here where we've got the curve crossing the x-axis. We're going to need to find this coordinate here later on. I'm going to call it A. We've got this point down here which I'm going to call C, okay, where P, that vertical line P from P, crosses the x-axis. And we're going to work out this area by integrating x times the natural log of x with respect to x between the limits a and c. I'm going to need to work out the coordinates of a in order to do that. Then I'm going to go on to work out the area of the triangle. I'm going to need to know this coordinate where the line L crosses the x-axis. I'm going to call this part here the point B. And in order to find out the coordinates of B, I'm going to need to establish the equation of L. Okay, so let's start first of all by getting the coordinates of A. And we do that by setting y on the curve here to 0. Okay, so let's just put that when x times the natural log of x equals 0. And we can see that we've got a product here equaling 0, so either x equals 0, so put therefore x equals 0, or natural log of x equals 0. And the natural log of x equals 0 when x equals 1. Well, clearly it's not 0 at A, that's the point, the origin here. A has to have an x coordinate, that is, of 1. So therefore we've got the A coordinate is 1, 0. Alright. So now I'm in a position to be able to work out this area here because I'll just integrate x times the natural log of x between A and C. That'd be between the x coordinate of 1, and we can see that the C coordinate is E0. It's got the same x coordinate as P. Alright. Anyway, we'll do that integral later. What I want to do next is establish the equation of the line L. So we'll just put here a subtitle for L. And to get the equation of L, I have a point on the line, the point P, E, E, that I can use as my x1, y1 when it comes to using the equation of the line in the form y minus y1 equals mx minus x1. But I need the gradient m, and I can get that gradient m by working out the gradient of the tangent of the curve C at the point P, and then applying the perpendicular gradient rule. So I need to get that general gradient on the curve C, and I do that by differentiating x natural log of x. And to do that, I'm going to need to use the product rule, which I'm assuming you're familiar with. If not, do check out my tutorials on it. Okay, so I take the x and multiply it by the differential of the other part there, natural log of x. The differential of natural log of x with respect to x is 1 over x. And then I plus, and then I take the other part, natural log of x, and I multiply it by the differential of x, which is just simply 1. And if I tidy this up, what we end up with is 1 here plus the natural log of x. So when I get the gradient of the tangent at P, that's when x equals e. And so when x equals e, I get that the gradient dy by dx is equal to 1 plus the natural log of e. And the natural log of e is 1, so we've got 1 plus 1, so that's 2. So that's the gradient of my tangent then at P. So I apply the perpendicular gradient rule to get the gradient of L now. So we'll just say that therefore the gradient of the normal, or just say gradient of L, okay, we know it's normal. So the perpendicular gradient rule is just to take the negative reciprocal of this gradient. So it's going to equal then minus 1/2. All right. So now I'm in a position to get the equation, I should say, of the line L. So therefore the equation of L is, okay, and so applying y minus y1 then equals m bracket x minus x1. So we've got y minus y1, so that's the e there, the y coordinate at P, equals the gradient, which is minus 1/2, times all of x minus x1, x1 being e here. Now I'm not going to expand that. All I need to do to get the coordinates of B, let's just say for B, okay, or I could say at B, for B, we know that the y coordinate will be 0. So I just substitute that into here, and I've got negative e equals, and I'm going to expand the bracket as well, it'll be easier, minus 1/2 x or minus x over 2. And then we've got minus 1/2 times minus e, so that's going to be plus e over 2. So I just need to rearrange this for x, and I can see that if I multiply through by 2, I'm just going to get minus 2e equals minus x plus e. And then if I add x to both sides and add 2e to both sides, then I can see that therefore x equals 3e. Okay, you might want to put a few more steps in there just to check it out. But I can see I'm running out of room, so that's why I just jumped a bit. Okay, so it follows then that the x-coordinate at B is 3e. All right, and the y-coordinate will be 0. Okay, well that's giving me the x-coordinates at A and B. So now I'm in a position to work out, let's say, this area here, this region APC. So we'll say area APC, and we get that area just by doing the integral of x times the natural log of x with respect to x, going between the limits from A to C. That's between 1 and e. Okay, so we need to do integration by parts here. So I'm assuming you're familiar with that. When you've got natural log of x, this is the u part, and the x is the dv dx part. Okay, so we take the u part, natural log of x, and we multiply it by the integral of the other part. So that's going to be x squared over 2. Then I subtract the integral of the part that I just integrated, which was x squared over 2, and multiply it by the differential of the other part. So differential of natural log of x is going to be 1 over x. And we integrate that with respect to x. And we'll just put in some square brackets here, because on the end here we put our limits. That is going from 1 to e. Okay. Now I can see that if we clean this up, we can divide that x into there. So we end up with a half x here. So I'm going to tidy up this first term. I'm going to put the x squared over 2 first of all. All right, x squared over 2, natural log of x. Now I've got to integrate minus a half x here. And the integral of minus a half x is going to be minus a quarter x squared. So we get minus a quarter x squared. I'm going to write x squared over 4, okay, instead. And we've got our limits that we've got to put in as well, okay, going from 1 to e. Just need to make our substitution now. We put e through, so we get e squared over 2 times the natural log of e, but the natural log of e is 1. So just get e squared over 2. Then substitute e in here, we've got minus e squared over 4. And then we subtract and we put 1 through. Now the natural log of 1 is 0, so that term goes. And we've now got minus 1 squared, which is 1 over 4, 1 quarter there. So what we have here is half e squared minus a quarter e squared, so that's going to be a quarter e squared over 4, same thing. And then we've got plus a quarter. So that's the area of our first region here under the curve. Now we need the area of the triangle CPB. So we'll just put that in here. Area of triangle CPB. And we can use the familiar half base times height formula. Half the base will be the distance from C to B. We know B has an x-coordinate of 3e from down here, and we know the x-coordinate of C is e, so it's 3e minus e, which is going to be 2e. And we've got to multiply it by the height, and the height is this height PC here, which is the y-coordinate of P, e. Right, and then we can just simplify this. The 2's cancel, so we're just left with e squared. So we now are in a position to work out then the area of R. It's going to be the sum of the two areas, so we've got e squared over 4, quarter e squared in other words, plus a quarter, and then plus this area here, plus e squared. And so you can see that if we group the e squareds together, a quarter e squared plus a whole e squared, that's 1 1/4 e squared. I'm going to write that as 5 e squared over 4. And then we've just got that plus a quarter. And that is in the form that we required. Okay, so you could write square units on the end because it is an area. All right, that's up to you. I prefer to do that, but you're not going to lose any marks if you don't do that. Okay, so there you go. Quite a long question. Hope you're able to do it. If not, at least see where you might have gone wrong. Okay, so for this question, this is a very basic one where we're given n in terms of t here, and we're asked to find n then at the start. So that's going to be when t here equals 0. So just a question of substituting t equaling 0 into that equation, and you're going to have 900 all over 3 plus 7e to the power 0. Well, e to the power 0 is 1, so you're just left with 900 divided by 10, and that's going to be 90. So therefore n equals 90. Okay, so for this question, we're given then n equals 900, all divided by 3 plus 7e to the power minus 0.25t, and asked to show that dn by dt equals n times all of 300 minus n, and that's all divided by 1200. So in order to do this, what we need to do, or we could do, should I say, is we could use the quotient rule, although I do feel that that's unnecessary, a bit long-winded, purely because in the top here we've just got a constant 900 rather than a function of t, like 900t for instance. So the way I would do it, which I think is quicker, is to rewrite this as 900 times all of that denominator. It's brought up to the top, and so we're going to have it to the power -1. And I can use the chain rule now to work this out. Chain rule you should be familiar with. It's going to be dn by dt is going to equal dn by du, as long as I multiply it by du by dt. It's as if these two du's cancel out. So I've introduced u here, and u is going to be this bracket here. So if I write that in, we've got u equaling 3 plus 7e to the power minus 0.25t. So that means that n now is equal to 900 times u to the power -1. Okay? So let's just border that off. And if we use the chain rule then, dn by dt is going to equal dn by du first of all. So if I differentiate n with respect to u, this is going to be minus 900 u to the power -2. And I can write that in then as minus 900, replace the u with what we have here, and it's to the power -2. And now we need to work out du by dt. And so if we differentiate u with respect to t, the 3 will go to 0, and then for this exponential function it will be the 7 multiplied with the minus 0.25. So I'm going to take the minus 0.25 as minus a quarter. So what we're going to end up with here is going to be minus 7 times a quarter, minus 7 over 4, and then it'll be e to the power minus 0.25t. Now, here comes the good bit. What we need to think about then, if we're going to head down to here, is to try and change this in terms of n. And I can already see that this looks very similar to what we've got up here, only I've got to the power -2. But I could expand this. I could think of this as this bracket to the power -1 multiplied by that bracket again to the power -1. Like this, okay? And also, we'll clean this up. We've got a negative here and a negative here. So that will be a plus. So if we rewrite that out again, you'll get this expression. So you can see that this bracket here to the power -2, I've written as the bracket to the power -1, and the bracket again there to the power -1. Okay, so how does this help us? Well, it just means that for the first part here, we've got this bit here, which I can see is this bit here. It's n. So we've got that as n. And for this bracket here, to the power -1, all I've got to do is divide both sides here by 900, so I can see that that bracket is n over 900. So let's just put that in as n over 900. And I'll put that all in brackets there. Okay. And then we've just got to take this part here. And, well, I've got to make the 7e to the power minus 0.25t the subject of this formula here, and I'll be able to get it in terms of n. So what I'll do is I'll number this equation 1. If I take that equation, first of all, let's multiply both sides by the denominator here. So what I get then is from 1, n times that bracket equals 900. And so if I now divide both sides by n, that'll be 900 over n, leaves me with the bracket, and then subtract 3, what I'm going to get is 7e to the power minus 0.25t then equals 900 over n minus 3. Now this would look better if I put this all over n. And if I do that, okay, we're going to get 900 minus 3n over n, and then I can pull out a factor of 3 and I get this result here. So when I go back up to here, I can see that all I need to do is multiply this result by a quarter. So what I'm going to end up with then is 3 times all of 300 minus n, and that's going to be multiplied by a quarter. It's just going to give me 4n there in the denominator. What I can see now is I can cancel. I can cancel that 3, for instance, with the 900, giving me 300. And I can cancel this n here with either that n or that n. Let's go for that one there, okay? And when I tidy this up, can you see now we've got the n times all of 300 minus n, all divided by 300 times 4, which is the 1200. Okay, so for this part of the question, we were given the equation here for n in terms of t, and we previously worked out the rate of growth, dn by dt, equaling n times 300 minus n all over 1200. And now we're told that that rate of growth, dn by dt, is a maximum when t equals big T here, after t months. So we've got to find out what the value of t is. And with this question, it's very tempting to put dn by dt, that rate of growth, equal to 0 and solve for n. Don't go down that avenue, because it's not dn by dt that equals 0, okay? That would only apply if we were told that n was a maximum after t months. That's when we would write dn by dt equaling 0. No, we're being asked to find that value of t when dn by dt is a maximum. So we could take this equation here and differentiate it again, put it equal to 0 and solve for n then, and then substitute that value back into here and work out the value of t from there. But it's much simpler than that. If we look at that fraction, n times 300 minus n all over 1200, it's going to be a maximum when the top of the fraction, the numerator, is a maximum. Because you're just dividing it by a constant here, so it's not going to change the fact that it's going to vary. So we're just looking for the top here then to be a maximum. And we've got a negative quadratic here if you were to expand this. And if you were to look at the sketch here of a negative quadratic like this, it would cross the n-axis when n is 0 or 300. And because it's meant to be a symmetrical graph here, then this maximum point here will occur halfway between 0 and 300, clearly at 150. And so when you look at this, you wouldn't necessarily need to write this down. This is what I'd be thinking when I see this fraction, that clearly that maximum is going to be occurring when n equals 150. So you could just state that. Saves you having to differentiate this again and put it equal to 0 and solve for n. It will turn out to be 150 though if you do it. Check it out if you like. So we're going to use that fact then that dn by dt, that rate of growth, is a max when n equals 150. So it's just a question then of substituting 150 into this equation here. So if I do that, I'll call that equation 1 and substitute t equals capital T here and n equals 150 into 1, then what I'm going to get is this result here. And so if I now cancel both sides, let's just do that, by 150, that's going to go once and that's going to go in there 6 times. And so what I could do now is multiply both sides by the denominator here, and doing that would lead me to this result. And what I'll do next is subtract 3 from both sides. That will leave me with 7e to the minus 0.25t equals 3, and then divide by 7, and I'm left with this result. At this point, all I need to do now is take natural logs to both sides, and that's going to lead to this result here. And we've got minus a quarter t, so I could actually multiply both sides here by -4 to leave me with t the subject. Doing that, I end up with this exact result. And you could leave it like that if you like, or you could just put this through your calculator, and if you put it through your calculator, you're going to get t equaling 3.389 and so on, which I've rounded to 1 decimal place, which is going to be 3.4. And remember, we're dealing with months here. So for this last part of the question, we're told that the maximum number of mice on the island then is p, and we're asked to state that value of p. So it's got to be pretty obvious. Well, I'm going to show you the thinking that goes behind it here. If we're to maximize this fraction here, then we've got a constant on the top and a variable quantity on the bottom. So in order to maximize that, we've got to make the denominator, the bottom of the fraction, it's got to be as small as possible. And because in this denominator we've got a constant here, 3, our only variable quantity is this value here, and we're adding it to the 3. So this has got to be as small as possible. So it just means that e to the power minus 0.25t, that's got to be as small as possible. And you should be familiar with that graph. If you've got a negative exponential graph, it's going to look like this. It's going to take on that kind of shape. And so you can see that it never crosses the or touches the t-axis. It just approaches it. So we can see then that for that smallest value, it's going to approach 0 as t tends to infinity. So it's just a question then of substituting 0 into here. And if you do that, then clearly we've got 900 divided by 3. And so that maximum value of n, which we call p, is going to be 900 divided by 3, which is 300. You could argue, though, that, remember, this only approaches 0. It doesn't actually equal 0. And since we need an integer value for the number of mice, okay, we could possibly take the answer 299. So either one of these answers is going to be acceptable. So there you go. Hope you've been able to follow that.